What if the key to staying alive after the world ends is something you've been flushing away your whole life? When facing complete resource depletion within approximately 48 hours before organ failure, an unconventional solution exists: purifying the water already within your body through scientific distillation methods. Directly consuming untreated urine proves fatal despite its high water content. While composed of roughly 95% water, the remaining 5% contains concentrated waste products including urea, mineral salts, bacterial contaminants, and metabolic toxins that kidneys have actively filtered from the bloodstream. Reintroducing these substances forces the renal system into an impossible workload, accelerating organ failure rather than preventing it. Military survival documentation explicitly categorizes urine alongside seawater and blood as dangerous fluids that worsen dehydration through their consumption. Each untreated sip concentrates harmful substances further, creating a deadly cycle where the body expends more water attempting to eliminate toxins than it gains from the liquid itself. Thermal distillation offers a proven method for separating pure water molecules from contaminated liquids. The process involves heating the liquid until vaporization occurs, capturing the resulting steam, and cooling it back into liquid form. This technique yields pure H2O, while leaving salts, urea, bacteria, and other contaminants behind. Astronauts aboard the International Space Station employ identical principles to recycle wastewater, achieving 93% recovery rates from all moisture sources, including urine. This same scientific approach remains accessible using improvised materials in emergency situations. Successful distillation requires three fundamental components: a heat source, a container capable of withstanding high temperatures, and a mechanism for capturing condensed vapor. Any metal vessel, discarded cans, damaged cookware, or scavenged containers serves as the primary boiling chamber. The contaminated liquid goes directly into this vessel without special preparation. A covering device creates the condensation surface where purification occurs. Scrap metal pieces, automotive parts like hubcaps, or even flat stones function adequately. The covering must be positioned at a slight angle to direct condensed droplets toward a single collection point. As heated vapor contacts this cooler surface, it transitions back to liquid form. This condensation represents the purified water output. The original contaminated liquid remains in the heating vessel while clean water accumulates separately. Various heat sources prove effective: open flames, portable stoves, residual engine heat, or concentrated solar energy. The objective requires achieving full boiling temperatures, not merely warming the liquid. Active boiling generates steam, the crucial element carrying only water molecules upward while leaving heavier contaminants behind. Visible steam production indicates successful molecular separation. Monitoring the condensation rate provides process feedback. Excessive dripping speed suggests the covering surface has become too hot to condense vapor efficiently. Absence of condensation indicates insufficient heat generation. Making gradual adjustments maintains optimal distillation conditions. This represents practical chemistry where molecular weight differences enable physical separation. Water vaporizes at 100 degrees Celsius while salts and urea remain solid or decompose without evaporating. After gathering sufficient volume, whether filling a cup, bottle, or other container, complete cooling becomes necessary before consumption. The purified water should be completely odorless. Any residual smell indicates contamination, likely from splashing raw material into the collection vessel, requiring the process to restart. Clean distilled water tastes characteristically flat and neutral. Testing a small amount first confirms successful purification before consuming larger quantities. Distillation functions through boiling point differentiation. Water molecules gain sufficient energy at 100 degrees Celsius to escape liquid form as vapor. Urea decomposes at higher temperatures without vaporizing. Mineral salts remain solid throughout heating. Bacterial organisms perish from thermal exposure and lack the properties to become airborne. Only water molecules possess the necessary characteristics to vaporize, travel upward as steam, and subsequently condense on cooler surfaces. The resulting liquid contains none of the original contaminants, just pure water molecules. This methodology underpins desalination facilities, distillation equipment for spirits, and spacecraft water recycling systems. The same physics and chemistry apply regardless of scale or sophistication, making the process achievable with rudimentary materials during emergencies. Theoretically, distillation could purify various contaminated liquids, though practical application should focus on available water sources. The concentrated residue remaining after distillation contains all removed toxins at exponentially higher concentrations, potentially 10 times stronger than the original liquid. This sludge requires careful disposal through burial or discarding far from living areas. Any contact between this residue and purified water reintroduces contamination, negating the entire process. Maintaining elevation for collection containers and precise angling of condensation surfaces prevents accidental mixing. Incomplete boiling fails to produce distillation. Merely heated contaminated liquid remains dangerous for consumption. Steam generation represents the essential requirement. Without visible vapor, purification cannot occur. Equipment used for distillation accumulates residual contamination, requiring thorough cleaning between uses, either through scrubbing or heating to sterilization temperatures, or substitution with fresh containers. Process errors carry severe consequences. Single mistakes, contaminated droplets, partial boiling, residue contact, result in consuming concentrated poisons. Without medical infrastructure, kidney failure becomes irreversible and fatal. Precision and careful execution determine survival outcomes. Successfully producing potable water through distillation demonstrates mastery over fundamental physical sciences applied to survival circumstances. Converting biological waste into life-sustaining resources represents practical alchemy, using heat energy and gravitational forces to separate molecules by weight. This capability persists regardless of infrastructure collapse, representing renewable survival knowledge, applicable repeatedly. When conventional resources disappear completely, scientific understanding provides alternatives that most consider impossible, transforming waste materials into essential supplies through systematic application of thermodynamic principles.